This is a short video explaining how to do the hypothesis testing assignment that you will see in week 8. So I'm going to open up Canvas, and I think I should share my screen with you. So you scroll all the way down to week 8. You will see the hypothesis testing assignment. This video will explain the first one, or I will use the data for the first one, but the process will work just as well for this one or this one. And so if you open it up, we will see we have some data for height in inches. And the question is, we want to know if the mean height for men in the US, which is 69 inches, we want to know if Troy male students are taller than average. So we're making a directional or a one-tail prediction. We think that Troy students on average are taller than 69 inches, at least the males. And so we've gathered a relatively small sample. And so this is the data that we need. I've actually copied it already. So when I open SPSS, I'll be able to just copy it straight in there. And again, you have to be a little patient with SPSS. So I'm going to paste the data that I already had. You will actually have to enter it. And I'm going to label it. So we have height. And it is numeric. And I want to make sure that I have the right scale. So remember, we have nominal and ordinal, sometimes called categorical. And then we have interval and ratio, sometimes referred to as numerical or scale. And so we definitely have ratio level data, which is scale level data. So I'm going to go back to my data view. And the first set of questions, I think up to question 10 or 11, ask you for basic descriptive statistics. So the mean, the median, the mode, the range, Q1, which is the first quartile, Q2, which is the second quartile, which is always the median, it's the 50th percentile, Q3, which is the third quartile, the IQR, which is the interquartile range, which is just Q3 minus Q1. It's the range for the middle 50% of the data rather than all of your data. So the range is maximum value minus the minimum value. The IQR is the 75th percentile minus the 25th percentile. So it gives you the range of the middle 50% of scores. Unfortunately, SPSS doesn't directly give this to you, but you only have to do one subtraction problem. Standard deviation, the variance, which is SD squared, and skewness. So we can do the first 11 questions with a press of a button. So we go back to Excel or StatCrunch, excuse me, and we go to Analyze. We click Analyze and we can go to Descriptives, and I'm going to choose Frequencies. I'm going to move my variable of interest over. I'm going to choose the statistics that I like. So I want the quartiles, Q1, Q2, and Q3. I need the standard deviation, the variance, the range. I don't need these yet. I need the mean, median, and mode. And I think I asked you for skewness, but not kurtosis. And kurtosis is how flat or steep, I know that's an oversimplification, but how flat or steep your data are relative to a normal distribution, whereas skewness gives us a measure of symmetry and is greatly impacted by outliers. So I've got my quartiles, Q1, Q2, and Q3, which is also the median Q2. And so I think I've got everything I need. So I hit continue and just okay. And so I know my mean is 70.87. So question 1, what is the mean? And I see 70.88, so that would round to this value. Second question, what is the median? And I see the median is 70 and the mode is 70. I can choose 70, mode 70. Next question, what is the range? The range is simply 82 minus 66. We don't really need a program for that, but you will see it clearly tells you what the range is, 16. So then it's going to ask for Q1, that's the 25th percentile. And so I see Q1 is 67.5. It's going to ask me for Q2, which is always the median. We already decided that was 70. And then Q3, the third quartile, the 75th percentile. And we know that is 72.25. And we need the interquartile range, which is literally 72.25 minus 69.5. And that gives me what? I may have coded this one wrong. I have to fix this one. So we've got, what did we say? 72.25. It's sad that I got to use a calculator for this. Minus 67.5 gives me 4.75. So Excel or StatCrunch, excuse me, SPSS does not directly give you the interquartile range. But all you have to do is subtract Q1 from Q3 and you've got it. So 4.75. What's the standard deviation and the variance? If you know the standard deviation, you just square it and you have the variance. And so the standard deviation is 4.96. If I square that, I get 24.69. So 4.97 and 24.69. Question 11, in terms of skewness, how would you describe your data set? So is it symmetrical? Do we have a dominant tail to the right? Or do we have a dominant tail to the left, which means we typically have an asymmetrical outlier or outliers to the right or left, or we don't have outliers. And so sometimes you can look at the data and you can easily see it's not symmetrical. In this case, I can clearly see that 82 seems to be somewhat of an outlier. We're going up by 1, 2, 3 points at a time, and then suddenly we make a 9-point jump. This guy seems to stand out a little bit. It's probably going to pull my tail a little bit to the right, but to be absolutely objective and empirical, I just need to get a value. And so if I go to skewness, anything other than 0 means it's somewhat skewed. Between -1 and +1 technically is okay. It's not perfect. So if we had absolutely no skewness, we'd have a value of 0. Since we have a positive value, we have positive skewness. It's not awful, but it's outside of, it's definitely not 0. And it's what some people call a normal range between -1 and +1. And it's even outside that. So I'm definitely going to call this one positively skewed. And that's what I expected with this value pulling things to the right. Next one, this is where hypothesis testing comes in. And so I am asking you for the null hypothesis. So remember, the null hypothesis always says the same thing. There's nothing happening. There's no difference between your means. There's no correlation between your two variables. Nothing is going to happen. There's no effect. Anything that you see in your sample data is simply due to chance. But in the population, there's nothing going on beyond what we expect to happen. Right? So in this case, the null would be, we don't expect Troy male students to be any taller than what we already know the population mean to be. So we know the population mean to be 69. So the null is going to say, I don't expect Troy students to be any different than 69. So that is this guy. Male Troy students have a mean equal to 69. There's nothing going on to make them different. Now, Some cases, we are almost certain the null is wrong. Doesn't matter whether we know it's wrong or not. Technically, it's always wrong. We still state the null as if nothing is going on. Right? So when we test the difference between men and women's heights, we know on average men are taller than women. But the null is going to say, even though we know it's wrong, there's no difference in height between men and women. So it's not what you expect to find or you think exists. It's always there is no effect. What is the alternative? So remember, alternatives can be one-tailed or two-tailed. So we know it's not this guy. This is our, excuse me, this is our null hypothesis. The alternative hypothesis, if it's non-directional, if it's two-tailed, is simply going to say Troy male students are different in height. They are not 69 inches tall. But we didn't make a non-directional prediction. We made a directional prediction. He thinks they are taller. So we need a statement, typically, but not always. The alternative hypothesis will be consistent with your research hypothesis, what you expect. Not always, but usually. So in this case, we're thinking they're taller. That's what we're looking for. And so we would say male Troy students have a mean height greater than 69 inches. If it was a two-tailed, we would just say male Troy students have a mean that is not, but we're making a one-tailed prediction, so we're going to say they're taller. Critical value. Critical value is the value that we must reach when we compute this t-value in order to reject the null hypothesis. So the critical value is directly attached to your alpha. For this class, unless I tell you otherwise, alpha is 0.05. So in other words, before we ever collect any data, we know we have a certain number of participants, we know we're going to need a value of at least this size or larger in order to reject the null. Now, in some cases, like a binary distribution, you can probably figure out the critical values by hand, but for the most distributions, we rely on tables. And so I'm going to exit this for just a minute. Actually, I'll reopen it so we have two of them open. I'm going to open a new window. I will go to another class where I have this table embedded, but it's also in this section. It's just called the critical values for the t-test. So I'll go here. I think I've got it embedded here. And so it will look like it'll be at the bottom of your Canvas page. And for this class, it's critical values for the t-test. So you actually have to open this table. It's probably worth printing it out and having it before you complete this assignment. To find the critical value, you need 3 pieces of information. So the first piece of information, in no particular order, am I making a one-tailed or directional prediction, or am I making a two-tailed or a non-directional prediction? We've already determined we're making a directional prediction. We're predicting Troy male students are taller than 69. Second piece of information you need to know is what your alpha level is. Unless I tell you otherwise, keep it at 0.05. So now I've got 2 things. I know it's a one-tailed. I know I'm going to test it at the 0.05 level of significance. And the third thing that we need is degrees of freedom. Degrees of freedom for the one sample t-test, and it differs for almost every test, so you just have to keep that in mind. But for the one sample t-test, it's n minus 1. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 pieces of data. Our sample size is n equal 8. So we know our degrees of freedom is 8 minus 1, which is 7. So I need this row. And I determined already it was a one sample or one directional at the 0.05, so it come down, and we need a value of 1.895. So in other words, when we compute our own t statistic, our test statistic, that's the value that we're computing, we know before we ever compute anything that we need a value of at least 1.895. Now, critical values aren't as useful as they used to be because computer programs will tell me the exact probability of my test statistic. But to me, I still find them useful, so I have an idea of what to expect before I ever analyze my data and start collecting my data. So let's go back here, and we agreed that we needed a 1.895. So we should see 1.895 right here. Now, we are going to compare our test statistic. That's the value that we compute. So when you see this TS, that stands for test statistic. This is the statistic we are actually testing for significance. And so go back to SPSS, analyze, compare means, one sample t-test. I'm comparing height, so I'll bring it over. And I'm comparing it not to 0, we know they're taller than 0, but the average height of males in general, which is 69 inches in the US. And make sure you have estimates of effect size computed or clicked, because that will give you Cohen's d. Cohen's d is a measure of effect size. So just because something is statistically significant doesn't mean it has real world implications. So you can think of effect size as analogous to practical significance, where our p-value is analogous to statistical significance. So I get a t of 1.067. We needed a 1.895. We failed to reach the height that we need to ride the ride, so we know we're going to fail to reject the note. We know this is not a statistically significant outcome, but we also know that when we look at our t-value, it's one-sided probability. 16% chance that this could have occurred simply due to random error when there's no effect in the population. That's too high. We want at least 5% or less. So we know we're going to fail to reject the no. We know it's not statistically significant because this is too high. We also know we're going to fail to reject and conclude that it's not statistically significant because this is too small. We needed the 1.867, I think it was, and we only got a value of 1.067. So this is what we're testing for significance, and we have concluded it's not significant. Chance is too much of an explanation for this finding. It doesn't mean there's not an effect. Remember, we only have sample data, so there really could be an effect. We never know for certain with inferential statistics, but we're pretty confident. So report your results in APA format. So had we just done this, and we did, how would you report it? So we know you always start off with a test, and the symbol for a t-test is a t, so that doesn't help us out. In parentheses, we will always get degrees of freedom. So we can rule out 8 and 8. So this is no good, and this is no good. So these are out. So the first one is always the test. The symbol for the test you're using, in parentheses with no space, is degrees of freedom. So we can rule this guy out because we know we had 7 degrees of freedom. When we looked up our critical table, we came down to 7 degrees of freedom, not 8. So we can rule this one out, and we can rule this one out. The third thing, so we get the test, degrees of freedom. The third thing that we'll see is our actual test statistic. Well, this is not our test statistic. Our test statistic is the value that we computed, and we computed a value of 1.067. So now we can rule this one out. The only one left over is this guy. So t-test was 7 degrees of freedom, and I actually need to put a space between here. I forgot to make it technically APA correct. Is 1.067. And the probability of getting this value, simply due to chance, where there's no effect in the population, is a probability of 0.16 or 16% of the time. But there is a decent effect size, but we wouldn't really worry about the effect size because we haven't even concluded that it's a real effect to begin with. So chances are you probably wouldn't see an effect size reported if your results weren't statistically significant, but I included it just to get you familiar with it. So Cohen's effect sizes, we have 0.2, 0.5, 0.8, and I think it's maybe a 1.3 or so forth, 1.2 for small, medium, large, and extra large. So this is, had it been statistically significant, somewhere between a small and moderate effect size. And we know that value from here. So one sample effect size, here's my Cohen's d estimate, 0.377. And so that's where I got this 0.377 from. What is the 95% confidence interval? So we go back, confidence intervals just give us a range. And I really like confidence intervals because I think they tell us more than just simply rejecting or fail to reject the null. So we know that our mean that we just computed probably isn't exactly the population mean, and we know we're the estimate that we've gotten. And so we computed a value of 70.875. So that's the mean for our sample. That is different than 69. But we're not interested in comparing our sample to a population. We're interested in going beyond that and saying, well, is the mean, the population mean from which this sample was taken, is that different than 69? And so because we only have a sample size of 8, we're not terribly confident that this is the actual mean. So we can actually put confidence intervals around that. And the way to do that is just add and subtract this from the value that you're testing. So if I take 69 and add 6 to that, 6.02, I will get my upper limit. And if I take 69 and subtract this value, I will get my lower limit. So that would actually give me the confidence interval for this sample mean. And as we can see, when we compute that, it includes 69. So we are going to take 69 plus 6, which would give us 75.02. So we go back and we see, yep, 75.03 right here. And if I subtracted that value, I would get 66.72. So if I take 69 minus 2.2796, I get 66.72. So that gives me a range of scores where I'm technically doesn't mean I'm 95% confident. Technically it means if I repeated the study 100 times, 95% of the time, my confidence interval would be correct and that it would capture the actual population mean. But for informal practice, you can think of it as I'm 95% confidence with this interval, I have captured the true population mean. So we know the lower boundary is going to be 66.72. So I'll go back and hopefully I'll see something that's legitimate. So this is my 95% confidence interval. What decision should you make? So remember from the notes, the nice thing about hypothesis testing is it's very simplistic in its outcome. You only get 2 choices. You can reject the null. If you reject the null, technically you're saying you had a statistically significant effect. You found something, you're pretty confident it actually exists, or you failed to reject the null. You don't accept the null, you don't reject the alternative, you don't accept the alternative, you're always testing the null. So when we say hypothesis testing, we are testing the null, and we either reject it or we fail to reject it. So in this case, we already knew we were going to fail to reject. We knew that for three reasons. One, our confidence interval actually contains the population mean. So we're pretty sure our sample came from a population that has a mean somewhere between 66 and 75. And guess what? That includes 69. We also know that we're going to fail to reject because our p-value was much too high. We wanted 5% or less. We got 16%, or a probability of 6.16. So we need a probability of 0.05 or less. And we also know we were going to fail to reject because we failed to reach our critical value. It's critical we reach this value. We only got this value. So we know we're going to fail to reject. If you fail to reach the critical value, fail to reject the null. What conclusion? So when I ask you what conclusion, I'm asking you, what does this mean that we failed to reject the null at the 0.05 level of significance? So if you go home to someone who's never taken a stats class and you tell them, hey, we conducted a study and we failed to reject the null hypothesis at the 0.05 level of significance, they're not going to know what that means. So what I'm asking you is to take this decision and tell me what it means in a real world statement. And for the most part, if you fail to reject the null, we don't accept it, but we're being forced to keep it. And what did the null tell us? The null said that we don't think they're any taller than average, which is 69. So the data did not support the claim that male Troy students are taller. It did not support that. And so the data do not support the claim that male Troy students are taller than average. In other words, 69 inches. So if you tell someone, hey, this is what we found, what did you find? Well, the data didn't support the claim that male Troy students are taller than average or different than 69. They're going to understand that. They're not going to understand fail to reject. So you have to be able to take this and translate it into something the average person can understand. That's what I'm asking by conclusion. Finally, this is something that is difficult for a lot of students to wrap their head around. Once you've made a statistical decision, you don't instantly know if you've made a good decision or not, because the whole point of this is inferential statistics. We're inferring something that we don't have. We're inferring something about something we don't have from sample data. So you don't survey 1,000 people and ask them who you're going to vote for in the next election and instantly know if you made a good decision or not. You have to wait for the election. So most of the time, unless you're just trying to confirm something, you truly don't really know whether or not you made a good decision or not until after the election or after multiple replications of the same study and so forth. So that's why I'm telling you if. So if we know reality, the election's already occurred, we know what truth is. So if I tell you, Troy male students are not any different, I don't know if they are or not, but I'm pretending that they're not. So if we assume this to be true, what type of decision have we made? So we can make a good decision called power. We can make a good decision, which is our confidence level, which is 1 minus alpha. We can make a bad decision. And that bad decision can be a type 1 error, or it can be a type 2 error. Type 1 error is a false positive. A type 2 is a false negative. And a good decision called power is when we find an effect that actually exists. So in this case, we concluded that Troy students are not taller than average. And now I'm telling you, as this omniscient being, that they are not taller than average. So our statistical conclusion has matched what actually exists in reality in the population. So that's a good decision when they match. So we can rule out these two errors. We didn't make a false positive or a false negative. We made a good decision. We didn't find an effect, and there was no effect to be found. It's like taking a pregnancy test and it says you're not pregnant and you're not pregnant, then you didn't find something and there was nothing to be found. I do apologize for the misspelling. I see that now. So this is a good decision called 1 minus alpha, or your confidence level. Hope this helps. I'll try to do another one for the second practice exam.